The objective of this lesson is to learn how to classify various types of chemical reactions. By the end of this lesson, you'll be able to identify a chemical reaction as one of 6 possible types. That is, as a combination reaction, a decomposition reaction, a combustion reaction, a single replacement reaction, a double replacement reaction, or is an oxidation-reduction reaction. Classification schemes play a critical role in science. To see what I mean by this, let's take a look at how you already use classification schemes in your everyday life in order to simplify it. Think about your last trip into a grocery store. Perhaps you needed only a few items and you were able to get into and out of the store in a matter of 10 to 15 minutes. Try to imagine what would have happened if every item in the store was randomly placed in the available aisles. Your 10-minute trip into the store would have become a nightmare. It would take hours, if not days, to find those few items you were looking for. Fortunately for consumers, grocery stores use a classification scheme where all food items have been classified by food type. For example, by produce, meat, dairy, snacks, etc. By classifying food items this way, you can predict where to find a particular item in the store. Classification schemes are useful in science because they allow us to simplify the world. When it comes to chemical reactions, for example, rather than thinking of every possible reaction as being unique and unrelated, we look for patterns of behavior that certain reactions have in common with each other. This allows us to group them based upon this common behavior. By understanding how reactions that fall within a particular grouping or classification will behave, we've not only reduced the amount of information we need to store about individual reactions within a particular grouping, we've accomplished something even more important. That is, the power to make predictions. Think about it. By classifying grocery store items by food type, you can predict where to find a particular item. In the same way, by knowing that certain reactants fall within a certain class of reactions, we can often predict what the products of that reaction will be before we ever perform the reaction. It's this predictive power in science that gives science this superstar status as a form of knowledge. When you think about it, science is the only form of knowledge in our society that has been successful at making predictions about the future. So let's now talk about a classification scheme we can use to identify a given chemical reaction and perhaps be able to predict the products of the reaction. As we said previously, in our classification scheme, we're going to introduce 6 classes of chemical reactions. It should be noted that these are not the only classes of reactions that exist, but these are the ones that we're going to focus on in this class. The first type of chemical reaction we'll consider is what we call a combination reaction, sometimes called a synthesis reaction. The word combination or synthesis means a coming together. We can write the reaction in the general form A plus B yields AB. Note that A and B are the reactants while AB is the product. So we can see what this looks like, okay, with this simulation here. So we have some sort of substance A, okay, coming together with a substance B to form the compound AB. While the reactants and products in a chemical reaction are always substances, for combination reactions, the reactants can be either elements or compounds that come together to form a more complex substance that is always a compound. So we can think of a combination reaction as 2 or more substances coming together to form a more complex substance. So we'll return to an example we looked at previously in the lesson on balancing chemical equations. Okay, that is the formation of acid rain. So this should look familiar here. As we can clearly see in this example, two compounds, that is sulfur trioxide and water, join together to form a more complex compound in the form of sulfuric acid. When we write a balanced formula equation, okay, it looks like this. Do you see how this fits the general form of A plus B yields AB? That is, two substances coming together to form a more complex substance. In this particular example, our two substances happen to be both compounds. But remember that in general, when we look at a combination or synthesis reaction, those substances can be either elements or compounds or a combination of both. So the second class of chemical reactions we'll talk about is what we call a decomposition reaction. Decomposition reactions take the generic form as follows. That is, we're starting out with a complex substance AB, which breaks apart into two simpler substances A and B. Perhaps a schematic will help you remember this. That is, a complex substance in the form of AB. So what we're starting out with, and perhaps through the addition of some heat or some other stimulus, we get this to break apart, okay, and in the process form two simpler substances we call A and B. Some things to note here. First of all, our reactant AB must be a compound because only compounds can break apart into simpler substances, whereas our products A and B, they can be elements or compounds. Do you see here how a decomposition reaction is really exactly the opposite of a combination or synthesis reaction? That is, in a decomposition reaction, we're starting out with a complex substance and we're breaking it apart into two simpler substances. Whereas with a combination or synthesis reaction, we're starting out with two simpler substances, joining them together to form a more complex substance. And finally, I can say here that when we're talking about decomposition reactions, predicting the products is not obvious. Usually some tests have to be done to be able to discern what those products are. So when it comes to the predictive power here, certainly experience helps, but it's often very difficult to determine what those products will be when your reactant decomposes. So again, we'll return to an example that we discussed in the previous lesson, the decomposition of calcium carbonate. In this example, we see that calcium carbonate, a single compound, breaks apart or decomposes into two simpler substances. In this case, two compounds, calcium oxide and carbon dioxide. Let's take a look at the formula equation here. You can see that this clearly fits the form AB yields A plus B, meaning that a complex substance breaks apart into two simpler substances. While the reactant must be a compound if it is to break apart, the products can be elements, compounds, or a combination of both. In this example, the products were both compounds. In the most basic sense, a combustion reaction is a chemical reaction where some compound we call a fuel reacts rapidly with oxygen. Fuels can take on many forms, but usually they are compounds containing the elements carbon, hydrogen, and or oxygen. A common subclass of combustion reactions is the complete combustion of hydrocarbons or carbohydrates. As Roadkill the lab rat is here to tell us, pure hydrocarbons contain carbon and hydrogen only, while carbohydrates are compounds containing carbon, hydrogen, and oxygen. When sufficient oxygen is present and the fuel molecules are not too big, complete combustion occurs, producing carbon dioxide in water as products. Incomplete combustion will occur when there is not enough oxygen or heat to allow the fuel to react completely to produce carbon dioxide and water. In this case, you get other combustion products, products we often consider to be pollutants. Some things to note about combustion reactions in general. Combustion reactions involve a rapid reaction of a compound with oxygen. When a pure metal slowly reacts with oxygen, as in the case of iron reacting with oxygen to form iron oxide or rust, for example, we usually don't consider such a reaction to be a combustion reaction because of its slow reaction rate. So, while having oxygen as a reactant serves as a major clue that you have a combustion reaction, also look for a fuel in the form of a hydrocarbon or carbohydrate as a reactant as well. So methane is the simplest of the pure hydrocarbons, consisting of a single carbon atom surrounded by 4 hydrogen atoms. Because of its small size, methane burns completely in a complete combustion reaction. We looked at balancing this equation previously, but now we consider it as an example of a combustion reaction. You can see that it clearly fits the form of a combustion reaction. That is, we have some sort of fuel in the form of a hydrocarbon or carbohydrate that reacts with oxygen to form carbon dioxide and water. The next class of chemical reactions we'll explore are what we call single replacement reactions, sometimes called single displacement reactions. Now, there are really 2 subclasses of single replacement reactions. The first being what we call metal replacement reactions, and the second being what we call non-metal replacement reactions. But first, a note about the symbols I'm going to use. I'm going to use the symbols M and M' to represent elements that are metals, while I'll use the symbols N and N' to represent elements that are nonmetals. Note that many but not all ionic compounds are formed when a metal joins a nonmetal to form a neutral compound. Let's start by taking a look at the form of metal replacement reactions. Our reactants consist of a pure element, a metal, I'll represent as M', and an ionic compound I'll represent as Mn. This is really all about the competition between the 2 metals. The stronger of the 2 metals, that is the more active metal, wants to be in ionic form and part of the compound. It would rather have a partner than be single. This means that if the stronger of the 2 metals starts out as a pure element, then because it is stronger or more active, it will be able to replace the weaker metal in the compound, forming a new relationship or a new compound. So as we see here, the pure metal in elemental form is the stronger of the 2 metals, so it will be able to displace the metal M, which starts out in ion form in the compound. When that happens, what starts out as the metallic ion will now become a pure metal, that is M, and what starts out as the pure metal will now join the compound in ionic form. If the stronger of the 2 metals is already in the compound, then no displacement occurs. So, for example, if we were to run the reaction in reverse, starting with M'N as the compound and weak little m as a pure metal, and we were to put them together, then no reaction would occur, since the stronger metal is already in the compound. Non-metal replacement works virtually the same way. But this time involving a competition between 2 nonmetals. The more active nonmetal gets to be in the compound. So if the more active nonmetal starts out alone in a single and elemental form, it will be able to displace the nonmetallic ion and form a new compound. And we see that is what happens here. So what starts out as a pure nonmetal in elemental form becomes a nonmetallic ion, and what starts out as a nonmetallic ion, that is N, gets displaced to become a pure nonmetal. Once again, if the more active nonmetal is already in the compound to start out with, then no displacement would occur. Some things to note about single replacement reactions. If you're trying to identify a reaction as being a single replacement reaction, note that they always take on the following form. The reactants are always going to consist of an element reacting with a compound, and the products will always be in the form of an element and a compound. Remember that we said in the previous slide that to predict the products of a single replacement reaction, you'll need to compare the strengths of either metals for metal replacement reactions or nonmetals for nonmetal replacement reactions. The activity series is a chart that can be used to determine which metal or nonmetal is the stronger, more active one. Remember that the more active metal or nonmetal wants to be with a partner, that is, to be in the compound rather than be single in elemental form. Alright, so let's take a look at a few examples involving single replacement reactions and see if we can predict the products of these reactions. In the first example, this is an example of metal replacement. We're told that zinc reacts with copper sulfate. So here, to see whether the reaction takes place, we need to take a look and compare the two metals in the problem. Okay, so we're taking a look here at zinc and copper. Now, since zinc is higher up in the activity series, meaning it's more active than copper, that means that zinc wants to be part of the compound. It wants to be an ion and be with the sulfate. So in this case, that means that the zinc can replace the copper. And when it does so, the copper ion will become elemental copper, will become a pure element, and the zinc, which starts out as a pure metal, will become a zinc ion and be part of the compound. In the next example, we're going to be looking at a nonmetal replacement reaction, so we'll be comparing two nonmetals, that is chlorine and bromine. When we take a look at where these elements fall in the activity series, we see that chlorine is more active than bromine. It's higher up in the activity series. Therefore, that means that chlorine wants to be in the compound, it wants to be in a relationship more than bromine does. So in that case, a displacement will occur and the reaction will take place. The chlorine will displace the bromine in the compound. So when this happens, okay, the bromine, which starts out in ionic form, becomes a pure element, and the chlorine, which starts out in elemental form, becomes part of the compound, becomes an ion. Of course, we need to add these coefficients of 2 to make sure that we have a balanced chemical equation. In the last example we're looking again at a metal replacement reaction between nickel and magnesium. Let's see whether the reaction occurs. So we start by identifying nickel in our activity series as well as magnesium. Now here we see that magnesium is the more active metal. It's higher up in the series. Since magnesium is already in the compound, okay, it already exists with the chlorine, no replacement is going to occur. So in this case we would write NAR, no apparent reaction. Okay, we do not get a reaction. Don't write the products in, which would seem to suggest that a reaction occurs if there is no reaction. The final class of chemical reactions we'll be exploring is what we call double replacement reactions, sometimes called exchange of ions, as you'll see shortly. Remember that single replacement reactions were characterized by a pure element reacting with a compound. Double replacement reactions involve a reaction between two compounds, usually, but not always, two ionic compounds. Once again, I'll represent an ionic compound in the form Mn to represent the combination of a metallic ion or positive ion with a nonmetallic ion or negative ion. Let's start by writing the form of a double replacement reaction. Then we'll explain it. So the reactants consist of two compounds. We'll say Mn and M', usually ionic compounds. If the reaction occurs, then there is an exchange of ions in the two compounds. That is, M and M' exchange places. When this happens, two different compounds are formed as products. Now, the way we write the reaction is really an oversimplification of what's truly happening. We need to look closely at the phase notation to understand what's going on. Let's start with the reactants. Writing Mn suggests that a compound exists where the two ions are somehow joined together. This may be true when the compound exists in solid form, but the symbol Aq means that the compound is soluble in solution. It means that the compound exists in a water solution. So what we really have is not Mn, but rather two ions surrounded by water molecules. The same applies to our other reactant, this other compound, M'N'. When added to water, it completely dissociates to form ions, one positive and one negative. So these two soluble reactant compounds dissolve in water to give us a bunch of ions floating around in a water solution. If a reaction is going to occur, then one of three possible situations must happen when the ions exchange partners. Each of these three possibilities represents a way for the ions to come out of solution. Otherwise, they're perfectly happy existing in their dissolved state. The first possibility is that when the ions exchange partners, that is, when M' comes together with N, a gas is formed which bubbles out of solution. There's the bubble you see. The second possibility when the exchange of ions occurs is that a solid precipitate is formed. This is a second way for the ions to come out of solution. Okay, that's not exactly what a precipitate looks like, but you sort of get the idea here. The third possibility is for a liquid to form, usually when a hydrogen ion from an acid reacts with a hydroxide ion from a strong base to form water. Now, the last possibility is what you see in the beaker. If all the ions are soluble and no precipitate, gas, or liquid water forms, then no reaction occurs. All we end up with is a bunch of ions dissolved in solution. Alright, so let's review some of the points we just made about double replacement reactions. First of all, when you're trying to identify a reaction and determine whether it's a double replacement reaction, note the form. All double replacement reactions involve a reaction between two compounds to form two different compounds as products. These compounds are usually ionic compounds. Double replacement reactions involve an exchange of positive and negative ion partners by two usually ionic compounds. The reaction involves at least one product coming out of solution by either forming a precipitate, a liquid, usually water, or a gas. Otherwise, all the reactants remain soluble and no reaction occurs. You can use a solubility chart to predict whether one of those products will be a precipitate. Alright, so let's take a look at some examples of double replacement reactions and see if we can predict the products of the reaction if a reaction indeed takes place. In the first example, we'll consider what would happen if aqueous silver nitrate is mixed with a solution of sodium chloride. If a double replacement reaction were to take place, then there would be an exchange of ions. That is, the silver and sodium would change places. So we can take a look at the potential products and see whether these potential products meet one of these three criteria. That is, do they form a gas, do they form water, or an insoluble solid precipitate? Let's take a look at our solubility chart to give us a clue. One of the products would be silver chloride, the other product would be sodium nitrate. Starting with sodium nitrate, we see that our solubility chart tells us that it's soluble. So that is not a way, sodium nitrate is not going to allow those ions to come out of solution. When we take a look at the solubility of silver chloride, however, we see that it leads to an insoluble product. Okay, silver chloride is a precipitate. This is a way for these ions to come out of solution. So yes, indeed, we actually will get the reaction to take place. Silver chloride here, we put the symbol S to show that it's a solid, okay, plus the aqueous sodium nitrate since it remains dissolved in solution. In the second example, we're looking at sulfuric acid being mixed with a solution of potassium hydroxide. Now in this case, if we try to predict the products here, we see that we're not starting with ionic compounds here, or sorry, the sulfuric acid is not an ionic compound, it's a molecular compound, but it behaves like an ionic compound. We can think of that hydrogen ion in the same way we think of a metallic ion. And if they were to change places, well, we need to take a look in our solubility chart at the solubility of potassium sulfate. Let's start there. We say yes, potassium sulfate from our solubility chart is soluble. And the other potential product would be HO, HOH, more commonly known as water. And we see yes, okay, we get a liquid formed as a product. This is a way for these ions to come out of solution. So yes, this reaction does indeed take place. We put in the coefficients here just to represent a balanced equation. In our third and final example, we're looking at a solution of ammonium nitrate being mixed with calcium sulfate. These start out as aqueous solutions. So let's take a look here. And in this case here, let's go ahead and write the potential products, okay, if there was an exchange of ions. That is, one potential product would be ammonium sulfate, while the other one would be calcium nitrate. Now, when we look at our solubility chart, okay, remember one of these products must be insoluble, or a gas, or water. Well, we know it's not water here. Let's see what our solubility chart has to tell us here. Okay, when we look at calcium nitrate, we see yes, it is indeed soluble. When we look at ammonium sulfate, we see that it too is soluble. That means that our criteria has not been met. There is no way for these ions to actually come out of solution. Therefore, no reaction actually takes place. No products are really formed. All we end up with is these dissolved ions that remain in solution. Now, I wrote the potential products here because I want to show you that we can't leave it like this. This actually misleads the reader and suggests that a reaction is taking place. Okay, so we don't want to write the products even though I would say writing those products may be part of the process to figuring out our answer. We don't want to leave them written. Okay, so in this case we would write NAR to suggest that no apparent reaction takes place. In double replacement reactions, cations and anions can come together to form an insoluble ionic compound, or hydrogen ions can come together with hydroxide ions to form water. There's another possibility, however. The ions can transfer electrons between them, producing what we call an oxidation-reduction reaction. These reactions are sometimes referred to as redox reactions to shorten the name a bit. So an oxidation-reduction or redox reaction is a reaction where electrons are transferred from one substance to another. Let's start by defining what it means for a substance to get oxidized or reduced. The substance in the reaction that loses electrons is the substance that gets oxidized. To make sense of the term, when a metal reacts with oxygen, it loses electrons in forming the metal oxide product, hence the term oxidation. The substance that gains electrons is the substance that is being reduced. Now, to help you remember this, think about an oil rig. Okay, in the word oil, you can think of this acrostic as oxidation is loss, meaning the loss of electrons. Rig refers to the reduction. Reduction is the gain of electrons. The law of conservation of charge tells us that charge cannot be created or destroyed in a chemical reaction. This implies that in any redox reaction, both oxidation and reduction must occur simultaneously, so that however many electrons are being lost by one substance, the same number of electrons must be gained by another substance. So let's start by considering the chemical reaction that takes place inside a fuel cell. This is the reaction that powers space travel, like that of all the space shuttle flights of the past. It is potentially the reaction that will be widely used to power automobiles one day, because as you'll notice in the reaction, there are no waste products. Water is the only product of the reaction. Okay, no waste products that we can consider to be a pollutant. And in the process of this reaction, a lot of energy is released. Given the reaction, we start by identifying the oxidation numbers for each element in the reactants and products. Remember that we can think of the oxidation number or oxidation state as the charge of the atom in an ionic compound. But for molecular compounds which don't form ions, we can still think of the oxidation state as a sort of apparent charge of each atom. If, for example, oxygen has a charge of -2 in the ionic compound magnesium oxide, we can still think of oxygen as having an apparent charge of -2 in the molecular compound water. Unless you're dealing with a species that is an ion where its charge is identified, you can assume that all substances are electrically neutral. That is, the number of protons and electrons must be balanced. So on the left-hand side of the equation, where we see the reactants taking the form of elemental hydrogen and elemental oxygen, these elements in their pure elemental form must have an oxidation state of 0. That's the only way they can form an electrically neutral compound. But on the right-hand side of the equation, when we look at water, if the oxygen atom has an oxidation number of -2, then each hydrogen atom must have an oxidation number of +1 in order for the compound to be electrically neutral. Once we've determined the oxidation state of each element in both the reactants and products, we are now in a position to see which element gets oxidized, that is, loses electrons, and to see which element gets element gets reduced. That is, the element that gains electrons. Starting with hydrogen, if each hydrogen atom on the reactant side of the equation has an oxidation state of 0, yet each hydrogen atom on the product side has an oxidation state of +1, then that means that each hydrogen atom must lose 1 electron in forming the hydrogen ion. Since there are 4 hydrogen atoms involved in this reaction on both reactant side and product side, okay, and on product side those hydrogen atoms have a charge of +1, that means that a total of 4 electrons were lost by hydrogen in this process. Let's now turn our attention to the other element in the reaction, that is oxygen. The oxygen starts out as a pure element, so its oxidation state as a reactant is 0, just like for hydrogen. In combining with the 2 hydrogen atoms to form water, oxygen ends up with an apparent charge of -2, just like the oxygen ion. To go from 0 to -2, each oxygen atom must gain 2 electrons. Since we have 2 oxygen atoms on each side of the equation, that makes a total number of 4 electrons gained by oxygen. So we see in the overall reaction that if 4 electrons in total are lost by hydrogen and 4 electrons in total are gained by oxygen, then while charge is transferred between species, no net charge is created or destroyed in the reaction, so the total charge is conserved. Because the hydrogen atoms lose electrons in the reaction, hydrogen is the species in the reaction that gets oxidized. Remember the oil in the oil rig, right? Oil, meaning oxidation, is loss of electrons. Because oxygen is a species which gains electrons in the reaction, oxygen gets reduced in the reaction. Remember the rig in oil rig. Reduction is gain. Now, we saw in our last example that what we classified previously as a combustion reaction is also an example of an oxidation-reduction reaction. In this slide, in this example, we'll see how a combination involving the synthesis of a metal and a nonmetal is also an example of an oxidation-reduction reaction, as one of the reactants loses electrons to get oxidized while the other reactant gains an equal number of electrons to get reduced. So given this combination reaction, where we have a metal reacting with a nonmetal, we'll look at the combination or synthesis of zinc chloride. Given the reaction, we start by identifying the oxidation numbers for each element in the reactants and products. Remember that we can think of an oxidation number or oxidation state as the charge of the atom in an ionic compound or is the apparent charge of an atom in a molecular compound. Both zinc and chlorine start out in elemental form as reactants, which implies that both zinc atoms and chlorine atoms have an oxidation state of 0. This is the only way that they can be neutral compounds. Remember that all substances are electrically neutral unless they happen to be strictly ions where the charge is given. When we look at the products where the ionic compound zinc chloride has been formed, we note that the chlorine atom, like all halogens, has a charge of -1, while the zinc atom must have a charge of +2 in order for the compound to be electrically neutral. Once we've determined the oxidation state of each element in both reactants and products, we're now in a position to see which element gets oxidized, that is, loses electrons, and to see which element gets reduced, that is, gains electrons. Starting with zinc, if each Each zinc atom on the reactant side of the equation has an oxidation state of 0, yet each zinc ion on the product side has an oxidation state of +2, then that means that each zinc atom must lose 2 electrons in forming the zinc ion. Since there is only one zinc atom involved in the reaction, this implies that 2 electrons in total were lost by zinc during this process. Let's now turn our attention to the other element in the reaction, that is chlorine. Chlorine starts out as a pure element, so its oxidation state as a reactant is 0, as we've already stated. In order to combine with the zinc atom to form zinc chloride, the chlorine atom first gains 1 electron to form the chloride ion. Since there are 2 chlorine atoms involved in the reaction, the total number of electron gains is therefore 2. So we see in the overall reaction that if 2 electrons in total are lost by zinc and 2 electrons in total are gained by chlorine, then while charge is transferred between species, no net charge is created or destroyed in the reaction, so the total charge is conserved in the reaction. Because the zinc atom loses electrons in the reaction, zinc is the species in the reaction that gets oxidized. Because chlorine is the species which gains electrons in the reaction, chlorine is the species that gets reduced in the reaction. So we've seen in the previous 2 examples that combustion reactions and certain combination reactions can also be classified as redox reactions. In this example, we'll see how single replacement reactions also fall under the umbrella of redox reactions. We'll consider the single replacement reaction between aluminum and copper 2 chloride. We know that since aluminum is higher on the activity series than copper, okay, that is, it is more reactive than copper, it will become an ion and replace copper in forming the compound aluminum chloride. As always, we start by identifying the oxidation numbers for each type of atom that exists in both reactants and products. So in this example, we need to consider the atoms aluminum, copper, and chlorine. Since aluminum starts out as a pure metal, it has an oxidation state of 0 as a reactant. But when it combines with the chlorine to form aluminum chloride, it becomes an ion with a charge of +3. This is because it has lost 3 electrons in forming the 3+ ion. Because we have a total of 2 aluminum atoms in the reaction, a total of 2 times 3 electrons, or 6 electrons, are lost in the process. In looking at copper, each copper atom starts out as a 2+ ion, since copper starts out in the ionic compound copper chloride. But you'll notice that each copper atom ends up as a pure metal with no charge for an oxidation state of 0. In order to go from a 2+ ion to a neutral element, each copper atom must gain 2 electrons. Since we've got a total of 3 copper atoms involved in the reaction, there are a total of 6 electrons gained by copper. The last element we need to consider is chlorine. Note that chlorine starts out as a -1 ion in copper 2 chloride and ends up as a -1 ion in aluminum chloride. So chlorine is what we would call a spectator ion, an ion whose oxidation state doesn't change in the reaction. It neither gains nor loses any electrons, in going from reactants to products. So we see here that, like all oxidation-reduction reactions, charge is conserved. That the element aluminum, loses 6 electrons in this process, while the element copper gains 6 electrons in the process. So we see that while charge is transferred from one species to another, the net charge is conserved in the reaction. So in this reaction, we discover that aluminum gets oxidized since it loses electrons, okay, while copper gets reduced since it gains electrons. And as we've already stated, the chlorine gets neither oxidized nor reduced in the reaction. Okay, and as we already stated, we noticed that in this redox reaction, as in all redox reactions, the total number of electrons lost is exactly equal to the total number of electrons gained. Okay, once again implying that while charge can be transferred among species, it is neither created nor destroyed.